Okay, guys, in the previous class, I covered the PD controller, and we saw that the PD, they are tuning the transient response, like as the P is affecting on the natural frequency of the system. And eventually you see that both, they're gonna stabilize the system in the next example. You saw that D added the damping to the system. By adding damping to the system, it covers up the lacking term S on that example. Then you can tune what the transient response of the system for transient response, which is critically damped, under damped or over damped system based on the demand of your boss. So being said, adding damping to the system, and as I showed you that the MP maximum overshoot you have in notes is minus zeta pi over 1 minus zeta squared. You can control what the maximum overshoot of the system if your system is under damp. The example of that, your car suspension system is a control system that has an under damp response. See here. So by adding controller, you can control this MP maximum peak, right? So in generally speaking, PD controller is tuning the transient or modifying transient response as we saw in the example, and we're continuing still today, plus stabilizer of the system. An example that we started the previous class and we're continuing today was the most favorite example, the particle pendulum. Even these days I'm teaching in the robotic class, that's right. And I want to keep it, as you saw, at desired angle of 45 degree, but in the MATLAB or Simulink we are showing as a radian, pi over 4. So, and as you saw in the MATLAB, in the Simulink, we go on MATLAB hopefully next week. So we had this theta d desirable angle, you have in your notes, in the unity feedback block diagram, and we added the PD controller, Kp plus KDS, refreshing your mind, and G, open loop transfer function, unity feedback, exactly we did in the Simulink. And we saw that the G here is 1 over, assuming M is 1, if I remember, L is 1 kilogram a meter, S square plus omega n square, right? The G is that for the pendulum. And you saw that without any controller, you have two pure poles on the imaginary axis, right? Like this. But after adding controller, and I said, and for example, I said your boss asked you to design a controller that is critically damped, which is zeta is 1, and I said omega n, if I remember, was root square of 12, if I'm not wrong. That's right, radian per second. Why? Because the pendulum can be counted as a 1 degree of freedom robot mounted on the rover on Mars. So you don't want to have a overshoot on the system. This is dangerous for robotic situations. You saw that by adding that, we had this profile. So, okay, this without controller was marginally stable. By adding controller, I mean this Kp and Kd that we designed, if I remember, Kp was 2 and the Kd was 4 root square of 3, right? Look at your notes and correct me. And this gave this, by Simulink that we did, right? Gave this, so this is pi over 4. I'm going to run it again. It gave this. So from margin stable system, we transferred to a stable system, but with a considerable what? Error signal. So we have to fix this. From marginally stable system, you came to the stable system, but with a considerable steady state error signal, E, right? I'm just refreshing. So, and you saw that we applied ESS to find E is Sx of S, 1 plus G, final value theory I taught you a million times, and I did in the previous class. This is pi over 4S, that's right. Input to the system, desirable input to the system, plus 1 over S squared plus omega n squared, right? S goes to 0. So what we got was, oh, this is new after designing controller. I'm sorry, guys. This is new. What's wrong with it? This is new. So here is KP plus KDS new, right, after adding controller. So if you put that, you're going to have pi over 4 and S0, this 0, going to be omega n square plus KP. Now, and I did in the previous class exactly. I played with the KP several times. I increased that as your friend said. And you saw that the E is decreasing. But this is not the solution. This is not a good solution. That's right. E is decreasing. Okay, because you are pushing the system to the high gain. This is high gain. High gain UR means that maybe your actuator is saturated. You are pushing a lot your actuator. In some point you get saturated actuator and your system won't work. This is not a good solution. I wanted to show this in the previous class. Not a good solution. Not a good solution. So now here I'm gonna teach you what gonna remove this undesirable steady state error signal E is I controller. So you know that I controller U over E that I told you is Ki over S. That's right, I controller. So being said, you're gonna have, I'm gonna put it here. Now, by adding I, we have PID controller. We had PD, we designed in the previous class based on your boss request. We did PD, but now we are adding I. So being said, I'm gonna add here plus, here's plus Ki over S PID. So I said steady state error signal. I'm gonna remove that. So the take-home message is this: PD dealing with the transient response. I controller deals with steady state response. Steady state response. How? By removing ESS to 0. Let me examine mathematically first. So ESS, after adding the controller, PID, now adding I, gonna be same. 1 plus nu G. That's right. So your nu G is this. Again, S pi over 4S divided by 1 plus Kp plus KdS plus Ki over S divided by S squared plus omega n squared. Good here, guys. This multiplied by this. This is your new open loop transfer function. G new PID. You got it, everybody? I just added I. So, can I go to the next page? This S with this S goes to hell, like previously. Is it desirable input that you want to follow? So, can I go? Yes, everybody?
Yes.
So ESS, steady state error signal, gonna be a limit of pi over 4, and here you're gonna have S square plus omega n square plus KP S plus KD S square plus KI divided by S. See here? This part. And this divided by S square plus omega n square. This goes to the denominator when S goes to 0. This goes to numerator, so we're going to have S square plus omega n square divided by, now this S cube plus S omega n square plus KPS plus KDS square. I have no notes, please correct me if I do something wrong. KS, and we have one S here, that's right? This S goes here when S goes to 0. Whatever it is, you have S0. Bingo! Made it 0. So you saw that adding I controller made steady state error signal to 0. Let's go to simulate. Validate for the very practical very practical example of the pendulum as a robot. File 13, and this is PD. I'm going to share this today with you because I'm going to be done with this PD controller pendulum. So sure. Oh, okay. Using the textbook terminology, G is of the plant here. The goal of J is to go from arbitrary to some kind of. What is GP? If it's possible to go from arbitrary PID to GP. What do you mean by GP? No, we are not going to. So I understand. So we are not going to reverse. What you are asking, if I understand correctly, you're asking me we design PID to go to a new plant. Okay? For simulation. No. We have the plant in the hand. Okay? Like a pendulum with some open loop transfer function. Okay? Now we are designing, is very, very good that you asked. Thank you very much. Okay? It's very good. Now we are designing controller to change, listen to me very carefully, to change the dynamics of the plant, not the plant itself. See what I'm saying? Okay. Yes. Okay. Changing the dynamics of the system. Not that you cannot change pendulum to, I don't know, pendulum plus. See what I'm saying? Okay. But you are, why you have to do that? Why you have to change the plant? But I mean, oh no, don't do that. So let me be clear. Okay. Let me go back to notes. Thanks for asking. That's a very good question. See, the whole story is very simple. Okay, this is the pendulum robot on the rover on the Mars, for example. You are applying the U from controller actuation to keep it here. That's it. Are you changing the physical robot? No, robot is the same. This is you that keeps it here, like as your shoulder joints. Your shoulder joints, if you want to keep it at 45 degree, your hand is a pendulum, that's right. Huh? Your brain, your brain sends signal to the joints of your shoulder to keep it at 45 degree, but it doesn't change your hand physically. See what I'm saying? So what you're asking, you're telling me we design a controller to give us a new hand. Why we need a new hand? Hand is hand. Mhm. Yeah, but see, what's your name? Jimmy. Oh. Without controller, the plant G is for this pendulum is S squared plus omega n squared. After adding the controller, your new Gn is this Kp plus Kds plus Ki over S in S squared plus omega n squared. But this, yeah, exactly. So tuning is a different problem, okay? As we are doing, but our tuning won't result in a new physical device. See what I'm saying? So you cannot change this pendulum to this. For example, this is for exaggeration, okay? You cannot the pendulum thing like this. See what, okay? So you cannot break it from here. Pendulum is pendulum. You are only controlling the position, angular position of the pendulum. That's it. See what I'm saying? So you are controlling exactly your AC unit, okay? Is a controller in your room, okay? In the California we have Nest company. That's right, Nest. Probably you heard that. Okay, Nest is kind of controller, simply PID controller probably. Okay, so they are only keeping your temperature of the room by tuning some parameters of the controller at 75 degree, but it won't change the room profile for you. See what I'm saying? Huh? So tuning, as we did, we tuned. Look at here in the previous class. By having this, we tuned KP and KD. See what I'm saying? Huh? Okay. So now let's go and add I controller. Where we are. Okay. Oh, not now. Open model. Bear with me. Okay. So so we developed in the previous class and saw even that we have to increase KP a lot to remove that steady state error signal, but that's a high gain and it's going to saturate your actuator. It's going to damage your actuator. This is not a good solution, as we discussed today. Come on. Yeah, also overshoots. So you see that? So we added PID here. Why is it slow? See, we see 2 and 4 square of 3. We saw that we can run it to visualize what we have done in the previous class. So is okay. Okay. Oof. Okay, so this is the blue line is the desirable input or 45 degree. And so that from marginal stable system without controller, we added PD is the stabilizers, but we have overshoot and the huge state error signal, even that we increased. If you remember that I did several times in the previous class to emphasize on that. If I increase even this to, I don't know, 50, um, it's not a good solution. There we go. It reduces that, but it's have overshoot this kind of problems and the high gain, and this is not good. So that's why, as I showed you by the final value theory, by adding I controller, I'm just putting Ki 5. Bear with me, okay? Just this Ki, see um, this I or Ki here, see? P, I controller, D controller. This is Ki. I'm putting 5. And then I'm gonna save this. And you see that, okay, what was your boss wanted to have, guys? He wanted to have a critically damped system. Zeta is 1. Means that there is no overshoot, right? Critically damped system that we discussed previously. So let's see what we have. Yeah, just let me show this, okay? Okay. Okay. So what is this? Okay. To 35 degree. And I increase this to another number. Okay. 10. Oh, this is because I increased the P. The original that we designed together was 2. I didn't change it. First let me show this and then you can ask question, okay? This is again 15. Okay. Here we go. See? So we have no overshoot and your bus satisfied. There's no overshoot here. Okay. And eventually goes to 45 degree. Obviously no radian. You got it, everybody? Let me finish this and ask question, okay? Now, if even that you want to see the error signal, copy paste because I'm going to show it with you, share it with you today. So here we go. Okay. And you see that the error signal finally goes to 0. Here we go. Starting from here, finally goes to 0. Here we go. So you see PD part stabilize the system, tune the transient response of the system, like avoiding the overshoot of the system. But I remove the steady state error signal, steady state, not vanishing. Error signal goes to 0 for the pendulum, a real physical problem. Okay, go ahead because I want to continue this. Go ahead. Here. No, that's the wrong logic. It's no one can do that. Except except you go to grad school and you have a course with the name of system ID identification, system ID in grad school. Okay. Yes, in system ID, you know the input coming to the system, not controller, input to the system. And you know how the system behaves, output. But you have no idea what's the model. It's a black box. In system ID, like as using the AI you are talking about, or regression, okay, regressor, okay, then you can estimate what's the model of the system, okay, from by observing what is input, what is output of the system. You can estimate what's the model of the system. But having controller in hand, you generate a plant, don't do that. This is wrong, very wrong concept. We are living in our planet Earth or in space around our planet. Okay, we have physical things in the hand, then we want to control it. We are not designing controller to generate a new plant. See what I'm saying? Okay, even if, yeah, yeah, no one would do that. Okay, that's a wrong logic. Okay, so guys, you saw that. Are you done? Because I'm going to continue. No problem, my duty. So you see that I selected Ki as 5, and it gave us whatever we want almost. We had non-overshooting, see, non-overshooting, kind of the critically damp, going to that, what we want. And now it's a trade-off. When you go graduate working for a company, name it from NASA to Johnson and Johnson, wherever you go, you can say, you know what, I'm going to increase this KI 35 to 35, see what happens. Hmm? So let me run it for you. Oops. You saw that such a drop on increasing before? No, you decrease that, but now you have what? You have what? You name it. You have what? Overshoot. Your boss say, I don't want to have it, man. I don't want to have overshoot. Okay? Finally, the steady state error signal goes to zero, but now you're experiencing overshoot. So it's a trade-off for you as a control engineer to see what you want from the system physically, what you want, how it behaves. See what I'm saying, everybody? Yes? So let's keep it to the previous version of that. Let's keep it to our pendulum as a 1 degree of robot to 5. I'm gonna back to this file. I'm not done yet. Let me back to notes. So here we go. Next page. Okay, 1. Eye controller removes steady state error signal. Bingo. We proved it by final value theory and we saw it by Simulink. What else? 2. Eye controller rejects disturbance. Reject disturbance. You're gonna tell me how, payment. Okay. Let me first show it to you how. Then I'm gonna back to mathematics. Here we go. If you remember, I was showing you the things. I'm saying I have a step disturbance here. Remember that I was plotting for you? Oh, what is this? This is disturbance to the system. U coming here, I'm just naming here to make sure. U of S from controller. And this is E of S. And now we have a step disturbance to the system. After controller, you have disturbance. Okay, disturbance acting on the system. Okay, and this is, I'm just typing here because I'm going to share with you this disturbance, and I'm gonna say keep it to, yeah, pi over 4, whatever. So now let me see how this, and you know what, the runtime is 15 seconds, that's right. I'm gonna say the runtime now is disturbance happens at 4 seconds. The step time is 4 seconds. Here we go. Now I'm saving it. Okay, and I'm running. Here we go. Oops. Guys, see? At 4 seconds, you have a disturbance here. See, exactly at 4 seconds. So the eye controller rejects it here. It said, okay, go to hell, I don't care. I want to go here. See what I have done? Now if I increase the disturbance value, huge one, 3. Just a huge disturbance in the system. Here we go. Oh, so you have a disturbance, and again, this rejects disturbance, finally goes to 45 degrees. Aside, everybody? Yes? And now, even that I go higher, I don't know, say 15. See? But finally, again, rejects that and goes there. Okay? The disturbance happens here. So, even that you change the time to 0, disturbance happens from the beginning, and this is, I don't know, is 2. It rejects this. There we go. The beginning rejects and goes again. Okay? So another function of the eye control is to reject disturbance of the system. You got it? Let's see what happens behind this, behind the mathematics of this. Guys, what's the name of this course? You tell me. What's the name of these courses? Huh? Linear controlled systems. Linear, not nonlinear. When you are working in the linear domain, you can apply superposition principle. Superposition. Any of you know what's that? Superposition principle. Do you know what's the superposition principle? Any of you? By any chance? So exactly. What? No. Who wanted you? Oh my god. Where's the white one? Let's at least do this. Okay. So yes, you can add things together. If you have x1 to the system, x2 to the system as input, x3 as the system, and xn as the system to a system, okay, you can say, you know what, first I want to have x1 only to have f1, then I'm going to only have x2 to have f2 to the system, then you have fn, then I can add the result together. I can say f total. This is a very simplified version of that. f1 plus f2 plus fn. For linear domain, you can do that. For nonlinear, no. You got it? So now, being said, let me go back to the disturbance, mathematics behind it. Look at here, guys. This is theta d, desired for the pendulum. Then you design controller as C, PID, controller C. Then I added a disturbance, D, being added to this plus. It went to the physical pendulum, G, and gives you theta. Unity feedback, assuming that you have ideal sensor. Okay guys, look at here. This is output of the system, real output. How many input now you have for the system? Look at the picture. How many you have in the system? Come on. How many input you have? One. Another input to the system? Two. You have two input to the system. But this is linear control. You linearized everything. Okay? You can say, you know what? Forget about this. I want to see effect of this on the output. Disturbance on the output. You got it, everybody? Simple. Superposition. Guys, remember I told you ESS by finite value theory is, they have your notes, S, E of S. Do you remember this? Which was limit of S as we defined 1 over G. I do care about this part now. Now you have Y of S here, output of the system. Now you can say, you know what, Payman? Y of SS final value, steady state when time goes to infinity, which here is angle SS, angle of the pendulum. Exactly, I'm going to use that S, Y of S when S goes to 0. I'm going to exactly use this by this input, not by theta d. I can do that. Final value theory can be used for any parameter. So let's find it. So this is Y, as I said, this is Y. Here I'm going to see signal B. I'm going to see signal U. And then I'm going to say signal M. And I said superposition. Okay, I'm going to delete everything here. The only input to the system is disturbance. Oh, sorry guys. Is disturbance. Here we go. So you see that Y equals to GB, as we did one time, very long time ago. B is what? Is D plus U. You see, we are not blind. D plus U. U is what? CM. But the M is what? You tell me. M is what? M is minus Y. Yes, minus Y. Exactly this. No magic. Okay? So I'm gonna implement this here. So you're gonna be minus YC. And I'm gonna put this here. This is gonna be D minus YC. And I'm gonna put this here. This is gonna be G D minus YC. And now I'm gonna take this out. I'm gonna find Y of S. Y gonna be 1 moving to the other side. GC, as we had previously, remember? GC, GD. So you can find from here Y is equal to GD 1 plus GC. Here we go. All right. Everyone agree? M is minus y, u is cm, gonna be yc minus yc. B is d plus u, gonna be d minus yc. And g in b, d minus yc. This goes to the other side, 1 plus gc, and here gonna be gd. You got it, everybody? So I'm gonna just exactly put this here. For the input of disturbance, by having PID controller, we added I. I want to see how much is the steady state of the YSS. Can I do that? Yes, I can. So YSS gonna be a limit of S, Y, G plant 1 over S square plus omega n square. 1 over S square plus omega n square. What is D? Disturbance was the step here. Say 1 over S. 1 over S divided 1 plus GC as we had previously. KP plus KI, KPS plus KD S square plus KI over S divided by S square plus omega n square. This with this goes to hell. This with this goes to hell. And S goes to 0. You're gonna have 1 over this S, okay? You have S here. And you're gonna have this C, S square plus omega n square plus KPS plus KDS square S square plus KI, and here's this guys, I made a mistake. KI, oh, I have to rewrite it to make a space here. Gonna be KPS plus KDS square plus KI over S. S goes to 0. Limit of this S goes above. S divided by whatever. What's the result? 0. Oops! Shows with the input of the disturbance, output is how much? Output is how much? 0. Means this disturbance has no effect on the output. By what? By I integrator that we added. You got the whole picture? Yes? You understand, everybody? Good. So now we learn that I controller removes the steady-state error signal and rejects the disturbance. Now, I told you the superposition. So total Y of S is gonna be, I'm gonna assume you have theta D here. I'm gonna say we don't have disturbance, total. Gonna be xg over 1 plus g. This is your x, that's right, remember, this is your x. And plus y of disturbance. Plus what? gd 1 plus, this is gc, I'm sorry. gc. This is your total y of s by accounting 2 inputs to the system. This is superposition principle. This is y of theta d. This is y of disturbance. What you saw I showed you by adding I, disturbance has no effect on the y. And that's why you see such a response in the Simulink. You got it, everybody? Next class, I'm going to show you a very special case of Ziegler-Nichols PID controller design for very special cases. Okay, I have to teach you. Okay, there are two tables I have to teach you. But before that, I want to go to MATLAB and develop a code embedding PID controller inside the code. Why? Because when you go to industry, you're going to deal with nonlinear systems eventually. If you go to grad school, you're going to see adaptive control, sliding mode control, MPC control, prescott time control, delay control system. These are nonlinear systems. You have to be able to develop a code and inside the code embed the controller, not only using Simulink. That's in the MATLAB. Before going to Ziegler-Nichols, I'm going to teach you how to embed PID controller inside the code and get the result. Just give me a second, okay?